Okay, it's 4 o'clock, so let's get started here. So project number 3 is due now. If for some reason you're unable to get it to me, let me know. I think I just got all the projects from everyone just in the last hour. So just looking ahead, I'm sure all of you are anxious to do project number 4 and get started on it. Tentatively, I plan to give it out on next Thursday. It's already written, but it relies on us covering this before you can actually do it. And the stuff that I highlighted there, as you eventually find out, is my interview seminar that I did here back in 2003 when I interviewed for the position. And it involved research that was eventually published in Biometrics in 2004, and this research involved the bootstrap. What you're going to do for project number 4 is reproduce my research, or at least part of it. So that's why I'm holding off on project number 4 until at least Thursday. My goal is for you to have this finished before test number 2 so I can grade it. I will give you project number 5 though before test number 2, but it will not be graded before you actually have test number 2. So, unfortunately, that's just the way it works out. Let's see. Are there any questions before we get going here? Okay. So we left off last time on page 65. I'm going to quickly finish up Chapter 3 notes and then get into Chapter 4. So we were talking about the jackknife after bootstrap. This is a procedure that's used to determine the sensitivity of our bootstrap calculations to whether or not a particular observation is in our data set or not. Obviously, we don't want our calculations to change dramatically from whether or not one particular observation is in the data set or not. One thing that we looked at, or one thing that the author suggests, is to, if you're interested in the bias of the statistic, look at the bias of the statistic, the estimate of the bias of the statistics without observation J versus with all the observations. So if you have a sample size of 10, that means you're going to have 10 different of these measures. And they suggest calculating this B sub negative J, which is the estimate, bootstrap estimate of the bias without the J observation, minus B, calculate or plot that versus the empirical influence values. And so what we're going to talk about today is how one can actually do this. It's not necessarily a canned, let's say, function that does it for you. And this is going to be in the context of Fret's head data. And that was a data set we were looking at a particular partial correlation. Okay. So, just to remind you what B negative J minus B is. Let me actually write it out. It's 1 over R sub negative J times the sum of the TR stars, and I'm just going to say the sum over all R's where no J, so no Jth observation, minus T sub negative J, so you calculate your statistic of interest, in this case a partial correlation, without the Jth observation. And we're going to subtract that from, or we're going to take minus 1 over R times the sum TR star minus T. So B sub negative J is on the left side, B is on the right side. We want to be able to calculate that. Okay. So here's how we can do it. We're going to use a for loop to loop over the J equal 1 to N observations. And in this for loop, we're going to calculate T sub J, T sub negative J every time, and put in something called T dot J. Notice while my code runs just fine the way it is, I thought there was a few changes there that, in terms of descriptiveness, would work. And also, this part right here can also be run outside the for. Okay? So T.J is just going to be a place where I'm going to calculate T sub negative j for every observation. So I'm going to initialize it to be numeric n. So in other words, a vector length n. T star bar dot j is also going to be length of n. And I guess to emphasize too, let me draw arrows to what those corresponding elements are in our formula. Okay. Now, if you remember when I calculate this b sub negative j stuff, I guess actually this portion right here, basically what that means is look at all your bootstrap observation, your resamples. And for those resamples that do not have the jth observation in it, calculate t star. So I need a way to determine is the jth observation in a particular resample. That's where the boot.array function comes into play. Remember, because that actually shows you which observations are in each resample. So if I take a look at this freak, make this a little bit bigger. So if I take a look at this object freak from boot.array, we can see that, for example, observation 1 does not appear in the first resample. It appears twice in the second resample. And what we'd like to be able to do is, when I calculate b sub negative 1, use this resample, use this resample, use this resample in my calculations. So, how do we do that? Well, let's loop over all of our observations. So I say for j in 1 to n. I'm going to take freak, comma, j equals 0. So notice when j is equal to 1, that means look at column 1. In other words, look at for y1, how often did it appear in each resample. For those times that it was equal to 0, meaning it wasn't in the resample, I would assign a value of true. For those times where it was in the resample, I would assign a value of false. So, for example, remember the first resample did not have y1 in it. The third one did not have y1 in it. So then when I combine that with boot.res $t, boot.res contains all of our bootstrap resamples from our last time, what's going to happen? It's just going to return what? The t stars for that do not have y sub j. Any questions about that? So that goes into an object I just call values. Then I find the mean of values. I put that in the jth spot of t star bar j. Okay. So t.j, remember I had a function called calc.t that actually calculates the partial correlation. We'll just do that without the jth observation. Then just combine stuff. So here is b sub negative j minus b, doing the calculations that you would expect. I'm going to plot these versus the empirical influence values estimated by the jackknife, and here's my plot. And here we go. Make that a little bit bigger. Similar to what we've seen before, I actually use the observation numbers for the plotting point, so it's more descriptive. And I know it's been a week, but you might remember observation 2 in our jackknife after bootstrap plot that we had, plotting other stuff. That one stuck out as affecting the quantiles of the distribution for T star. What kind of effect does this have on the bias? Does it have a large effect or small effect? Small. So it's interesting here, with respect to the bias, it's not going to really play that big of a role. That's a good thing. We don't want stuff to affect our calculations. So observation 14, overall, if you look at it in terms of absolute value of these b's and negative j's minus b's, is the largest. It is 0.017. And if you translate that into then, or take into account that the bootstrap estimate of the bias is 0.0014, that means then that without observation 14, the bias changes to 0.0184. Okay. Is this something to be concerned about? You have to put it into the context of what you're measuring. You're measuring a partial correlation. So think of it maybe just in terms of regular correlation, between -1 and +1. If someone told you the correlation was 0.3, and then without a particular observation was let's say 3.1 or 0.32, would that bother you at all? Probably not. So what we have just seen here, even though that this observation 14, is the largest in absolute value, it's not that big of a deal. It's not going to affect our calculations with respect to the bias. Now, obviously, too, you can do other plots like this for other measures, too, not just the bias. Okay. I think I already mentioned this paper by Davison, Hinkle, and Ventura. Section 310.2. I strongly considered adding this section to my lecture notes this semester. Basically, what it gives you is a way to figure out, this goes back to section 3.9, figure out, well, what kind of transformation should I use with T so I have a variance stabilizing transformation? And they use a Box-Cox transformation with a regression model to help figure that out. I was able to, when I was starting to write everything up for these lecture notes, I was, of course, trying to reproduce an example. I was able to reproduce about half of it, but not all of it. I can't figure out what I'm doing wrong, or if maybe they're doing something wrong. I don't think they are. It's just maybe my misinterpretation. And I eventually got to a point where I couldn't spend any more time on this. So, if anyone is looking for extra credit, come talk to me. And if you can reproduce their example entirely, I would be interested in giving you extra credit. We can negotiate the amount of extra credit. Okay. Section 311, choice of estimator from the data. You can read this on your own if you're interested. It's just kind of interesting section that says, okay, let's say if you have maybe more than one way to estimate a parameter, or something else that you're interested in. For example, maybe you have method of moments estimators versus maximum likelihood estimates for a particular parameter. How do you choose between the two? The Bootstrap gives a way to do it. You're welcome to read that section, but you're not responsible. Okay, that concludes chapter 3 then. Okay, so chapter 4, hypothesis tests with Bootstrap. Actually, I would say that most of my research, when it involved the Bootstrap, has involved hypothesis tests of some form. And I guess you could even say I've come up with a new bootstrap procedure myself for a particular problem. I didn't name it the builder bootstrap, but I named it the gains bootstrap after the motivation of this paper that I used to motivate how I approach the problem. One of the difficult parts of bootstrap hypothesis testing is the fact that in regular old hypothesis testing, you assume that HO is true. So you're assuming then that you have some distribution, let's call it F0 or FO for HO, where the actual samples are coming from. Well, you need to reproduce that then when you take your resamples, and this can be tricky. Okay? And you'll see examples of that coming up. So section 4.1 in the book, please read this on your own. It's just kind of a review of hypothesis testing at the level that you would have seen in Stat 883. Depending upon what you got out of 883, this might be more of a help to some than others. Just a few points, just so that we can talk about stuff in section 4.2 here. Again, we assume that the null hypothesis is true, so we're actually sampling from F0. We're going to measure some kind of test statistic T. Notice how I'm using T here for the test statistic of interest, which is kind of like how we did for chapters 2 and 3, but it wasn't necessarily a test statistic. And what this T is trying to do is measure the discrepancy between the data and HO. And you can think of it like a regular old t-test for testing a population mean to see how that measures the discrepancy between the data and the null hypothesis. Again, little t will be the observed value of the test statistic. In the book, they typically look at situations where only large values of t indicate evidence against HO. Where does that appear? For example, like with a likelihood ratio test. It's large values, like an F test in a regular old ANOVA situation. But we all know that there are situations where both small and large values indicate evidence against HO. Think of a two-sided t-test. And so I will discuss what you can do in those situations, even though the book really doesn't talk about it too much. Well, there's even cases where only small values indicate evidence against HO as well. For example, if you've ever heard of p-value combination methods, this appears sometimes in meta-analysis situations where you're combining results from multiple studies by looking at their p-values and assuming that the studies were independent of one another. You can combine those p-values and take advantage of now a larger sample size overall because there's multiple studies, and then look at that to make a determination, and through these combination methods, maybe simply the product of the p-values, for example, small values now indicate evidence against HO. Because, of course, a p-value itself, the smaller it is, the more evidence against HO. So a p-value provides then a measure of how much evidence exists against HO. How do we calculate a p-value if only large values indicate evidence against HO? You're doing this in the context of our notation. Probability that random variable t is greater than or equal to the observed value of your test statistic given F0. And we call that p, or p-value. Under HO and a continuous t, p, if you think of p, the p-value as a random variable itself, has actually a uniform 0-1 distribution. How many of you actually saw that in 883? You think so? Anybody else ever seen that? Anybody else ever heard of that before? And it's an interesting concept to think of your p-value as actually a random variable. But if you think of, let's say, repeating your sampling process and performing hypothesis tests every single time, it's a random variable. And in fact, when you do Monte Carlo simulation studies, sometimes people will actually look at, let's say simulating data under HO and look at all the p-values, look at histogram. If the histogram is uniform in shape, great. If it's not, you might worry. P-values can also be defined in terms of condition on sufficient statistics. Again, a topic that's often taught in 883. We'll look at actual condition on sufficient statistics as well later on in this chapter. Okay. So we're going to talk about, I basically combined two sections in section 4.2 that we're going to focus on. Monte Carlo tests and parametric bootstrap tests. That's what the authors call them. I will just simply refer to this as the parametric bootstrap in terms of hypothesis tests. The authors make a small, they talk about the difference, but there's this very, very, very small difference that I don't think it's really worthwhile saying, okay, this is Monte Carlo test versus this is parametric bootstrap. Most people, I can just call this a parametric bootstrap. Okay. So, we again assume that y1 through yn comes from f0. That means for a parametric bootstrap setting, we need to resample from f hat 0. So f0 will be a parametric distribution. So let's say if your hypothesis is that mu is equal to 0, let's say, and you hypothesize you have a normal distribution. That means f0 then would be normal 0 sigma squared. F hat 0 would be exactly the same thing, normal 0 sigma hat squared, which I guess actually I'm getting into the next example already. But you have to be careful about what you use as an estimator. So, testing mu from normal. If we just said that the null hypothesis itself was mu is equal to mu 0, that's what I wrote this example up on. And so what do we do with this, the sigma hat squared? This is often referred to as or sigma squared itself is often referred to as a nuisance parameter because it's not involved in the actual test itself, but we still need to take care of it somehow. So it's a nuisance. But what could you do? Well, maybe you could just use the regular old unbiased estimate for sigma hat squared, for sigma squared itself. We call that sigma hat squared. You could do that. But if you and if HO was true, of course, then that's going to give you an estimate for what sigma squared is under the null hypothesis. But you could actually go further if you wanted to and actually use this estimator instead, which incorporates the actual null hypothesis itself. Why am I dividing by n instead of n minus 1 then? I haven't estimated the mean. Yeah. So you could do that. And you'll see people do both. I would expect this alternative way that I had circled there perhaps might end up being a little bit better in terms of the size of the tests, in terms of power. Those are, of course, the two ways that we typically evaluate hypothesis tests, size and power. Okay, so what does the authors refer to as Monte Carlo Test? Well, in their definition, f hat 0 would not depend upon any nuisance parameters or the corresponding estimates, where the parametric bootstrap would depend upon some kind of nuisance parameters. I don't think it's really enough to make call something one thing and call something the other thing. I'm just, again, going to call them parametric bootstrap. So how do we do this? It's not, the idea is not too difficult based upon what we've done, previously. Simply, of course, go out and actually go take your sample and calculate t, whatever your statistic of interest is, which will be a test statistic. Then take our resamples from f hat 0, obtain your resample data, as we have used previously in terms of our notation, and then calculate your p-value. again, what we want is this p-value. How do we estimate it? Well, it's called the estimate of p star, and find the probability that t star is greater than or equal to the observed test statistic value given sampling is coming from f hat 0. This is what you would expect. Alternatively, you could define your notation like this, of course. Probability star, t star greater than or equal to t. Now, when you're actually doing resampling, then you estimate this p star with this. 1 plus the number of these t stars that are greater than or equal to t divided by r plus 1. So all this is just a measurement of how extreme you are in the distribution. So if this is what our histogram of all the t stars looks like, and let's say t happened to fall right here, you're just finding the proportion that are over here, essentially. I'll explain why there's a 1 here. It's similar, somewhat of a similar explanation to, I guess, chapter 1 when we were looking at quantiles. Somewhat. Now, our book will call this p star. Are these two p stars exactly the same? No. So, maybe it might have been better to put a hat on there. I'm just going to be consistent. In the context of what we do, it will make sense. Okay, are we taking resamples or not? As long as R is large, you're going to be just about the same. Now, what happens, though, if, let's say, both small and large values indicate evidence against the null hypothesis? So you're not necessarily saying it has to be greater than your original test statistic to reject HO. Well, there's not necessarily a unique way to define a p-value in this situation. And this is the best one, generally speaking. Take p star to be equal to 2 times the minimum of how extreme you are on the right-hand side of the distribution or how extreme you are on the left side of the distribution. That's it. 2 times the minimum. 2 because it's 2 tildes. You will see another way to calculate a two-sided test p-value later on. How do we actually do this in terms of resamples? Well, as you would expect, basically you're counting the number of t stars that are greater than t or less than t. Okay, so, comments. The p-value gives a measure of how extreme observing t would be if HO was true. So all you're doing is replacing, let's say, like the t distribution for a t-test. You're just replacing it basically with a histogram. And you're looking at where does your test statistic fall on that histogram. That's all you're doing. So why the +1 in the numerator and the denominator? Well, if HO was really true, then the original t itself would be just one more piece of information about the null distribution t, right? Okay, so r plus 1. Also, t is always at least as large as itself, so 1 plus it. And there you go. The book gives a little bit more precise reasoning. It's not really that big of a deal. In fact, you will probably more often see people use this. The number of t stars that are greater than or equal to t divided by r, if we just have a one-sided test. So it's not big of a deal because, of course, r is going to be large here because you control what r is, and so we're going to get just about the same. Okay, now that leads us to an example. As what is often the case with examples from the book, you think it's a fairly simple example to, at least the first read through, simple example to understand what's going on and what's it about. But then when you actually try to replicate it, you start seeing small little things like, oh, I have to do this, or oh, I have to do this. And as you will see in this particular example, it takes me 13 pages to go through all of it. So I think it's a good example in terms of how to apply a bootstrap to a situation that you probably have never encountered outside of this class. It also gives you some experience with common statistical things that are needed in terms like estimation and problems that can occur with estimation. And so that's why I do want to go through all this example, even though it will take about half a class period to do. So we're going to work with the air conditioning data once again. And we're going to basically do like a likelihood ratio, as I say there, like test to make a decision. The decision is between two different distributions for what? Null hypothesis, y is gamma. Alternative hypothesis, y is log norm. Seems like a reasonable thing that someone would want to investigate. Often in similar types of situations, then, since we have parametric distributions, one would perform a likelihood ratio test. Here's how the authors define a likelihood ratio like test statistic. Again, they call it T. They take 1 over n times the log of, let's let 1 correspond to the log normal, and 0, or O, correspond to the gamma. So log of, the numerator is the likelihood function for the log normal. The denominator is the likelihood function for the gamma. So, taking into account what a likelihood function means in terms of just a product of density functions, I can write this as the sum of the log of f1, the density for the log normal, divided by f0, the density for the gamma. And again, using some more properties of logs, this is I guess you could say, the final result for what the test statistics would look like. Now, this is similar to a regular old likelihood ratio test-like statistic. Of course, negative to log, we often use lambda to mean the ratio to likelihood functions. So if you were to do this in this situation, this is what we would get. And so you can see what the authors are doing. Essentially, they are taking this negative and they're distributed through. So that's why we have F1 here, F0 here, and we have a negative here now. And instead of using a 2, which of course is just a constant, we're not using any kind of chi-square distribution approximation here, so big deal, I have a constant there. So instead they just decided to replace the constant with 1 over n, which you don't really need to do, but that's what they did, as a way to say, okay, I have the sample size of n, so we'll put that in there. And so that gives you some justification for why they're using a little bit of a different test statistic.
Is there a typo in your very first -2 log stuff? Should the top one be L1 and the bottom one be L0?
You right here?
Yeah.
No, because, sorry, and I should have mentioned this. Normally when you do a likelihood ratio test statistic, you have the null, the likelihood function under the null divided by the likelihood function under basically the alternative.
Right.
And so the null is represented here, the alternative is represented there.
Your null is the gamma?
Yeah.
And your gamma is parameterized kappa and mu.
Oh, okay, I'm sorry.
I was going based on, I was going based on the parameters, but so the parameters are actually what's flipped.
I was going by the subscripts, not the parameters. But yes, you are correct.
I was trying to get my subscripts to match my parameters, and I wasn't sure which way they had gotten flipped, whether the parameters were flipped or the subscripts were flipped. So.
Flip the parameters.
Okay.
Thank you. That's what happens when you copy and paste without paying as close attention as you should. Perhaps you've run into the same problem sometimes. I'm talking about in general, not necessarily. Okay, so then the big question, why can't we use the usual chi-square approximation here? Hopefully you don't see my comment. What's that? You don't need to start with the normal, because remember it's just asymptotic. Perhaps all of you looked at the notes now after I mentioned that. Well, what do we normally have with respect to the hypothesis? We have a certain property with respect to the hypothesis when we do a equilibration test. The null hypothesis is nested within the alternative hypothesis. Is a gamma a special case of a log normal? Nope. So, it's not a regular old equilibration test. Can't use chi-square approximation. So that's one of the reasons why I wanted to do this, because it was different. Okay. So to do this hypothesis test now, I need to resample under the null hypothesis. Again, the null hypothesis is a gamma. So to resample under the null hypothesis, so in other words, to find f hat 0, I need this to be a gamma kappa hat mu hat, right? Now we saw in chapter 2 how to find MLEs for a gamma. We used the optimum function, if you remember that. So there's not closed form expressions for the MLEs, so we're going to do that again. However, we run into a problem that often occurs, especially you see this more in simulation studies when you have so many data sets that you're trying to evaluate in terms of, in this case, find maximum likelihood estimates. Remember with a gamma, your parameters have to be greater than 0. When I was applying the stuff, or the function that I developed in chapter 2 with optimum, I was sometimes getting, with my resamples, negative parameter estimates. Can't do that. So I use what's a common trick to counteract these kinds of situations. What you can do is find the parameter estimates for log of kappa and log of mu. So you can call this, let's say, mu prime and kappa prime. Of course, now since you're using the log, those could be negative. But then to get it back into the kappa mu scale, when you use the exponential function, what happens? You're guaranteed to always have positive estimates. It's just a common trick people use to do this. Not just this, but in similar kinds of problems where stuff needs to be positive. Also, in this code coming up, you're going to see me do some comparisons to the asymptotic distribution for these maximum likelihood estimates. And since we're working with the log scale now, I needed the log kappa hat, log mu hat asymptotic distribution. And again, what we typically learn in an asymptotic course, this quantity here converges in distribution to a normal random variable that means 0, because maximum likelihood asymptotic bias, and then work with a Fisher information matrix inverted as the covariance matrix. We can estimate then the Fisher information matrix with what? The inverse of a Hessian matrix. Based upon your observed data, you get the Hessian matrix. Remember, optimum actually automatically produces that for you, so you don't have to worry about derivatives yourself. And then one can actually use what's called the multivariate delta methods then to find just the covariance matrix for kappa hat mu. You're going to see me do this in the program. You're not responsible for it, but it's a nice little tool, statistical tool, to know how to do. So I could also use the boot function then to take my resamples. As remember when I first did parametric bootstrap, I said it's often just easier to just use the like an R gamma function to do the sampling, and then I will use the apply function then to get my T stars out. Okay. So here's my data. We've seen it before. Sample size is 12. I will need the MLEs for a log normal. Because remember, I'm going to need that for my test statistic T in the end. And that simply, alpha hat is the log of y sub j. I didn't write that very well. One can show it's just the mean of the log data. Beta hat is now basically just the, I'm not going to write it up, it's just the sample variance, but now for the log data. I'm sorry, the bias sample estimates for the bias sample estimate of the log data. And you can see that from my expression there. Now, since I'm going to have to iteratively find my MLEs for my gamma, I can start with method and moments estimators first. It's my initial estimates, and then let Optum actually help me find my maximum likelihood estimates. In my Optum function itself, this is on page 410, Optum, remember how it works. First, you put in initial estimates of your parameters. And notice what I'm going to do here. I'm going to say log of par.gam. So par.gam contain my mums. And then since I'm going to work with the log, because of this problem I told you about, I'll use the log function there. My function that's going to calculate my log likelihood function. In other words, actually it's going to calculate the negative log of L. Remember, Optum finds the minimum versus the max. If I find the minimum of a negative log L, that gives me my maximum of my log L. This function that I'm going to show you shortly contains the negative log L. I'm going to have to pass in my data to the function, just some controlling aspects of iterative method, in terms of iterations, Hessian equal true to give me my estimated Hessian matrix out. So let's look at my log likelihood function, or negative log likelihood function. I don't know, just as a way to show you how useful various versions of R help are. When I was first programming this in a few years ago, I was looking to see if somebody had some good solutions to the problem that I was having with negative parameter estimates. And I came across this listserv post, and I just simply copied and pasted their code directly. I could have modified for purposes, but just because for emphasis, I just copied it directly into my program. They called their function gamma log like, passing parameter estimates, data, and then they have some other argument that we'll talk about shortly. So, log of capital, log of mu, here's my log likelihood function. Now, remember with the log likelihood function, let's call it L, you're taking the log of the product of some densities, or equivalently, you're taking the sum of the log of the density, right? Well, in R, for most densities, you have D gamma, there's always an argument called log, since we often want to work with logs when we do maximum likelihood estimates. So log equal true allows me to avoid having to say log of D gamma. There perhaps may be computational advantages to doing that. I wouldn't be surprised. I don't know for a fact if there are, but I wouldn't be surprised if there are. So d gamma data, that's my x argument. I didn't put x in there. Shape parameter corresponds to our alpha. And notice what I do here. I use exp log kappa. Scale parameter corresponds to our beta, exp of, and I take into account how r parameterizes. And by using the sum, then I get my log likelihood function. So this evaluates for the 12 observations, essentially. And taking the sum, then sums all these log of densities up. And lastly, here, return the negative log likelihood function. You could have just simply put negative LGLK. I guess the author of this function wanted to be a little bit more fancy. And it says, if negative is true, return the negative log likelihood function. Otherwise, return just the likelihood function. Take into account that typically you're going to want to do this with the optimal. It's not a big deal. It's just what they do. Any questions about that? Okay. So, of course, whenever you program something like this, you just test it out. So, for example, I tested it out with the method moments estimates. See what would happen with my air conditioning data. I get a log likelihood function, a negative log likelihood function of 67.69. Now, as a way to check my result, when I do optim, then I need to make sure that I get a value of my negative log likelihood function, which should be similar, but of course it should be less, since I'm working with negative log likelihood function, it should be less. Because, of course, maximum likelihood estimates maximize the log likelihood function. Any questions? So, run my code. So, here is my maximum likelihood estimate for the log of alpha, maximum likelihood estimate for the log of beta. Negative log of L is 67.64. Notice how that is indeed less than what we would get from the moms. It's in the same ballpark as you expect. Convergence equals 0 means yes, it did converge. If it was something else, we would get problems. It did not converge. And here's my estimated Hessian matrix. Put it into the scale of kappa and mu. Kappa has 0.7. Mu has 0.08, which matches what we had in Chapter 2. Yes? I'm sorry, what? For the, did you say the covariance matrix? The Hessian matrix? Well, here's the Hessian matrix. So when I invert that, I get the estimated covariance matrix of log of kappa hat, log of mu hat. And I probably said this in Chapter 2. Maybe you'll run into this in your research. If you use optim, this is going to greatly simplify your life because you don't need to figure out all the second derivatives yourself by hand. Typically in your research, you're going to be working with something a lot more complicated than the gamma. You don't need to find then the second derivatives by hand and actually program it into a software package. Just use optim. Has made my research life a little bit. So, actually, I guess I did do this. Here is then the estimated covariance matrix. Without going into the details then, you can use the multivariate delta method. And eventually come to a point where you find, here, I'm not going to write it out, the estimated standard deviation of kappa hat and the estimated standard deviation of mu hat. Now we can get to some reasoning. Let's just take R equal 999. just to reproduce the book. Similar to confidence intervals, you may want to take a larger value. It depends upon where your test statistic, though, is on the distribution. So if you want to get a good estimate of the p-value when the p-value is going to be small, of course, take a larger number of samples. But then again, before you do the hypothesis test, you don't know if your p-value is small or not. So usually just take a large number of resamples. So to take my resamples then, I use the R gamma function. N times R are the number of resamples because sample size is 12 and I want 999 resamples with placement. My shape parameter is kappa hat, scale parameter is mu hat. And then here's my first resample. So I put this all into a matrix, a 999 by 12 matrix. So what I would like to do now is calculate T, my test statistic, for every single row of that matrix. So use the apply function. Apply, here's my data, y0.star. I'm going to apply this by row. The function I want to apply per row is this function I call find.est. Find the estimates, find T. No, I'm sorry, just find the estimates. Then later we will actually find T. So again, I had to write another little function to do this. You can kind of see why this is all kind of long. So essentially, how we found the maximum likelihood estimates before, I need to put this all into one function. I find my moms, put them into one vector, use the optim function. I also need to find my maximum likelihood estimates for the log normal. And what I return are 5 different things. Maximum likelihood estimates for the gamma. I also save the convergence, let me know if I actually did reach convergence or not, so that's obviously important. You don't want to use cases where you don't have convergence. And then also then the log normal estimates as well. So why do I need this? I need these for every single resample so I can calculate T star. Here are the just a second. Here are the first 5. So this is for R equal 1, R equal 2, and R equal 5. Here is, let's see, kappa hat star, mu hat star, convergence criteria, alpha hat star, and beta hat star. Now, based upon my prior experience when I was using my original function from Chapter 2 to find the maximum likelihood estimates, I was worried about, do I have negative parameter estimates? That can't happen here now based upon my function, but I just included the check anyway. Let's sum up all the trues and falses from checking whether or not a kappa hat star is less than 0. I did 0 times. Same thing for mu. Let's check my convergence criteria. Again, this is going to be a bunch of 0s and 1s, so let's sum them up. Great, everything converged. So that's good. Just throw this out there. If I didn't have convergence at some time, what would I do? Excuse me?
You would not include it when you're doing your calculations then?
Yeah, I wouldn't include it when I'm doing my calculations. Now, oftentimes this is going to happen when you're doing research and you're writing a paper about the results. Of course, you need to then state in the paper these many data sets, or in this case, resamples, were excluded because this happened. If this happens a lot, then you might have problems actually being able to present them in the paper. Just to make sure that it's clear, because I once had a PhD student who did not know that he needed to state that. Anyway.
If you have a whole bunch that don't converge, could you go back and change your iterations and perhaps then hope that they converge?
Well, you can basically rethink your simulation study. And it depends upon what you want to do. If this in particular is a method that you're putting in your paper and you're wanting to show that that method's not as good as your method, well, then you include it and say, oh, look, it doesn't work here. That's why my method's better. But if it's your method that's proposing and you don't get convergence half the time, an editor is going to say, I don't think your method's worthwhile for me to publish. Okay, so let's look at a histogram of our parameter estimates, the kappa hat stars and the mu hat stars. And also I'm going to throw on top of there at the asymptotic normal distribution so we can see what it would look like. This is what we get. Well, if you didn't look at this, here I would ask you, well, why do you think normality's not working here? Well, remember, you get a small sample. Maximum likelihood estimates are asymptotically normal. We have a sample size of 12. Here are the histograms for the log normal. Notice it's not normal as well. I guess I could have found the asymptotic distribution. Okay. Let's see here. We are on page 13. We're almost done. So finally, I need to calculate t. So how do we normally calculate t? You write a function called calc.t. Before I get into that, though, let me show you how I try to calculate t for every single resample data set. As you might expect, I use the apply function. And what I'm going to do is create an object called each zero, or each O, meaning each data set resample under HO is going to be in there. So this each O is going to be right here. So, for example, this is going to be Y11 star. This is going to be Y1, 12 star. But also at the very end, I'm going to put the maximum likelihood estimates too. So this is going to be kappa hat star 1, mu kappa hat star 1, mu hat star 1. This is going to be alpha hat star 1 and beta hat star 1. So I have three things around my mathematical symbol. Could get worse. I could have some pre-subscripts or pre-superscripts, but I don't have that. So I just put this all into one matrix so that I can easily use then the apply function. So for every row, let's say margin equal 1, I'm going to apply calc.t, also passing the sample size. So that in calc.t, I have something called alt. This corresponds to every row of my each zero. The first n rows, of course, are the data. So I put that into data. I pull out kappa, mu, alpha, and beta. In other words, do kappa hat stars. Kappa hat star, mu hat stars. corresponding to their corresponding to their column. Of course, remember, the apply function just throws in one row at a time, so that's why I don't need to specify particular row numbers. And then I calculate my test statistic finally. Just as a reminder, here's what the test statistic looked like about 10 pages prior. Right there. So it's just a matter of putting into the correct syntax this test statistic. So notice what I do here with the log normal function. With the log normal density, there's a DL norm function that calculates the density. And notice I use log equal true because of this part right there. And then I sum it, so I can find the sum across all observations. I then subtract the corresponding D gamma part and multiply by 1 over. And just for fun, to show that indeed that you do get exactly the same answer, here is the usual -2 log lambda statistic as well. Okay, so now finally I have all my T stars. So, of course, let's do a histogram. So I do a histogram the usual way. Often when you're doing hypothesis tests using the Bootstrap, it's nice to actually put the observed test statistic itself on the histogram plot so you can visualize what that p-value is going to be. So I take my observed value, which I calculated and put it into T here. So I just applied calc.T with my observed data. And I use the text function to allow me to actually write on the plot with the value of T. If you wanted to, let's say, maybe I should have done this, if you wanted T outside of the actual plot itself, you can use a function called mText. And I think we looked at that function before. It stands for margin text. Put some text out the margin. Okay, so from that plot, you can see that it looks like the test statistic kind of falls roughly in the middle of the distribution. And if you calculate the p-value then, and notice how I do this, I take each of my T stars, that's the first column of what I had calculated, and I check, is it greater than or equal to the observed value of T? And so I get a bunch of trues and falses. Using the sum function, it transforms the true and falses to ones and zeros. So that allows me then to find how many times the T stars are greater than the observed value of T. Combine this up with a 1 plus in the numerator, and R plus 1 in the denominator, I get 0.381. If you were to use the usual old likelihood ratio test statistic, you get, of course, exactly the same thing. So, do I reject or not reject HO? I don't reject. And sometimes when I say that to my studying 70 students, I wonder if they know to reject when the p-value is small, because usually I have blank stares. They missed out on their first stat course. How do you determine to reject them? That's not really worthwhile for me to mention that here, but I did, due to some frustration I had recently. Anyway, so the book, of course, ends up getting something different in this case. They get a p-value of 0.62. So who are you going to trust? You're going to trust me, or you're going to trust Davison and Heatley? Well, after spending a lot of time, I cannot find anything wrong with my program. And what's interesting, the authors, and I'll explain this coming up on the next page, the authors actually do the test a different way using a student-test statistic, and they get a p-value of 0.34. It's kind of close to 0.38. And they remark about, well, geez, this is kind of strange. Our p-value from this approach here, I got a 0.62, but using a different approach, I get a lot different. And I still don't reject HO, but I get a lot different. So what I hypothesize is that perhaps their calculated p-value was incorrect. In fact, probably what they did was turn that around, or did something to the same effect. I could be wrong, but I think I am right in this. Okay, so that's how you would do a hypothesis test in this situation. You can now think about how you would do other parametric bootstrap hypothesis tests. Approach it in the same manner. Now, in the book, they do mention using this studentized statistic. And they say it is difficult to derive. And they present new information about how it is done. Now, as I say here, I am not sure how it's derived then either. Normally you think of a studentized test statistic like this. T minus theta divided by the square root of E. In this particular case, what to use for theta? Normally we have a hypothesized value of our parameter. We don't really have that here because we have distributions. And they're not nested. If you have any thoughts, please let me know. So I haven't been able to do that. I've looked, did like a quick little literature search to see if anybody's approached this problem too and come up with something. And I have not been able to find anything. So then the authors end the whole problem like this. It should perhaps be mentioned that significance tests of this kind are not always helpful in distinguishing between models, in the sense that we could find evidence against either both or neither of them. This is especially true with small samples such as we have here. In the case of the reverse test, meaning change HO and HA, just flip them. In terms of put log normal in HO, gamma in HA, you don't reject HO as well. So this is a problem that you have with doing hypothesis tests with these hypotheses. Now, you might think, well, maybe we should even do this particular example then. I like the example because it's a problem that you don't normally see, and it has some good examples of what to do in a parametric situation. So that's why I chose to still reproduce their example in the book. Okay, so section 4.2.4 and section 4.2.5 we're not going to discuss, but they're still interesting topics. Section 4.3. We will stop right here since we're running out of time. Just a little introduction. We're going to do non-parametric permutation tests. Some people call these randomization tests. I think most people now call them permutation tests. There are actually whole books on permutation tests. One that I recommend is Jim Higgins' 2004 book. Higgins was my non-parametrics instructor. He was at Kansas State. I took his course in fall of 1995, and he was actually just starting to write his book at the time. And he would basically write a chapter and give us the chapter. Notice it took him 9 years to get it published. As some of you know, I'm actually writing a categorical book right now, and I started in fall 2010, and still not done. And I hope my book doesn't take that long to write. Anyway, so his book is Introduction to Modern Non-Parametric Statistics. The reason why it's called modern is because in a traditional non-parametrics class, before computing power really got to the point that it did, I guess, start in the mid-90s, and now, obviously, definitely now, the traditional non-parametrics class, which most students would have, would consist of normal distribution approximations to statistics. And in fact, I don't know, maybe this is, I don't know if this is the case or not. Has anybody taken step 874 here? Non-parametrics. Okay, sometimes it's offered as a summer course. I think.
It wasn't.
Is it still taught from the point of view you're doing normal distribution approximations for stuff, you're not actually talking about permutation tests?
We did some.
You did some? Okay, that's good. I know at least a few years ago when I talked to Ken Estridge, who was teaching, he did some the old normal distribution approximations. But anyway, there's no reason to do that kind of stuff now because we can just simply use computing power to do the permutation tests. With Higgins and some other students, I took, because we really liked this class, I took a readings class from him on the history of permutation tests. It's very interesting to look back in the 1920s and 1930s about how people were thinking of simple, tests for mean or other simple hypothesis tests, how they had thought about doing the problem, and that is they would essentially, it's not exactly what we're doing here, essentially use a bootstrap. But they couldn't do it because they didn't have the computing power. So they said, okay, well, let's do this normal distribution approximation stuff. And so it will be interesting to see where statistics would have went if back then they wouldn't have the computing power to do the stuff that we do now. And that now, we know, well, let's just simulate the distribution. And it's becoming just more and more and more prevalent. And not just here, but even in cases like Bayesian statistics where you simulate a distribution. So anyway, for a few of you who took me with Stat 875, we talked about permutation tests with respect to a Pearson test statistic. We will actually do that again, but talk more about why we do what we do. If you took categorical from me last spring, unfortunately we did not get to this particular test, so that will be new to you. Okay, so we've got 2 minutes left. I don't think it's worthwhile to get into a whole section then, so let me just call it a day. Are there any questions? Okay, that's it for today.